next we're going to see how we can use the derivative to help us find some convenient approximations. We're going to see two different approximations. The first is called the linear approximation, also known as a tangent line approximation. So here we're going to start with a function, and we're going to mark off 2 points, a and x, and we're going to say this x value is near this a value. But the setup is going to be, we know this function evaluated at a. So a standard example, the first one we'll do is approximate square root of 9.1. Well, we know the square root of 9. But we want to know square root of 9.1. So we know what happens at a certain value. We'll call that a. We know f of a. Period. We want to know f of x, and x is close to a. Well, how can we use calculus to help get an idea about what f of x is? Well, we know that with calculus we can find an equation for this tangent line. And because of that, we can find the tangent line evaluated at x. So here we're going to note this value, this y value. So the y value on that ordered pair. This y value gives a reasonable approximation of f of x. If x is close to a, it gives a pretty good approximation of f of x. F of x meaning this y value. So maybe I'll just call this function f. I shouldn't have said f of x there. We have that function f. We know what happens at a. We want to know what happens at x. But what we're going to do is travel along the tangent line and find that value. And that value does give a reasonable approximation of the value we want. Let's define that a little more formally and then do some examples. Definition: if f is differentiable, so derivative exists everywhere, then we may approximate f near a using the line tangent to f at a. Well, that's what we did there. We can approximate f near a using this tangent line at a. And right here, this equation gives us our x values. It gives us an approximation for this x value. The left side of this equation, sorry, I should have said this y value. The left side of this equation is that point up there. The right side of this equation is this point down here. And these are not equal, so we use the approximately equal to symbol. F of x approximately equal to f of a plus f prime at a times a change away from a, times x minus a. And we call this equation, this right side, we're going to call that a function. We're going to call it capital L of x. Here we have, I believe I have not used this notation. This is a computer science symbol, colon equals. I don't know what language, I don't know anything about languages except I think this is in Java. Maybe it's in C or whatever the other ones are. But right here, colon equal means we're taking by definition, or we're defining. So here, colon equals. Here we call L of x defined to be this approximation at a given x. We call L of x the linear approximation of f of x at the point A. Linear approximation, or sometimes called linearization. And notice that this equation up here is just a rewriting of a tangent line. So let's do a couple examples. example. Find the linear approximation. So find L of x of f of x equals root x at what? At a equals 9, and use it to approximate root 9.1. And here I'll give you the actual value and the approximation, so you can see that this approximation is pretty close. Find linear approximation of this. Well, we need that function down there at a equals 9. So we need f of a, which is 3. We need f prime of a, and we need x minus a. Well, there's f of x, so what's f prime of x? I'll say f of x equals root x. F prime of x, what is that? Well, it's half x to the negative half, or 1 over 2 root x. We need to evaluate these at 9, so I'll just say, so f at 9 is 3. What's f prime at 9? 1 over 2 times 3, 1/6. And now we can find our linear approximation formula. So L of x equals, maybe I'll write it like this for the first one, f of 9 plus f prime of 9 times x minus 9. So there's the formula with a equals 9. Well, we have the numbers here. So f of 9 is 3, f prime at 9 is a sixth, times x minus 9. And notice that is an equation for a line, because it's just what numbers with an x to the first power. So right there, we answered the first part, find the linear approximation. You don't have to simplify, you don't have to combine numbers. You'll see, so if you did simplify, you'd get, what, a sixth x plus 1.5 or something? But our goal is to use this equation to give us an approximation. And we'll see that leaving it like this is going to make the simplification of the approximation much easier, because we're close to 9. 9.1 is very close to 9, so if we let x equal 9.1, so L at 9.1 equals what? 3 plus a sixth times 9.1 minus 9. Wow, what's this? It's 3 plus a sixth times a tenth, which is 3 plus a 60th. This one does happen to, you could, 3 is 180 60ths. So this one, writing it as one fraction isn't too much of a chore. But in general, I would accept an answer like this for one of these. So here we have 181 60ths. Now, I'll just note, comparing the decimals, the approximation we got, 181 60ths, is approximately equal to, what is it, 30167? 3.0167, and the actual square root of 9.1 is approximately equal to 3. Maybe I should write it so it's not like the same vertical line. Square root of 9.1 is approximately equal to 3.016620 approximately. So this approximation does give us a pretty good approximation. Notice also, square root of 9.1 we would expect to be a little larger than 3. And right here, we see that our answer is a little larger than 3. It's 3 with another 1/60th. What if I changed this example? In your notes, it might be good to not rewrite the same example or not do exactly what I'm about to do. Maybe just say, next example, same thing with 8.9 rather than 9.1. Same thing with 8.9 rather than 9.1. What would change? Well, L of x would be the same, but how would our answer change? Maybe I'll just do it like this. L of 8.9 equals 3 plus a 6th times 8.9 minus 9, which is 3 minus 1/60th. That's negative 1/10. Negative 1/10 times the 6th, negative 1/60th. So notice, built into this approximation is, in this x minus a term, a negative will show up if what we're looking at is to the left of what we know, and it'll remain positive if what we're looking at is to the right of what we know. So square root of 8.9 we would expect to be a little less than 3. Square root of 9.1 we would expect to be a little more than 3. And both hold true with that approximation, or with this linear approximation. Let's do 2 more approximations, 2 more linear approximations. Let's do negative. Let's do natural log of 9. Natural log of 0.9. I guess I didn't have to erase all this. Yeah, let's do different directions for the next one, because those directions have a lot of words. Use a linear approximation to approximate log of 0.9. Natural log of 0.9. I'll write it here. Use a linear approximation to approximate log of 0.9. Now, in the first example, we said, I gave you the value we knew. We knew that we were looking near 9, because 9 was the value we knew. Well, log of 0.9, what number near 0.9 do we know the logarithm of? Well, we know logarithm of 1. Logarithm of 1 is 0. So here we're going to let f of x be log x. Then f prime of x is what? 1 over x. F of 0 is log of 0, which is 1. Oh, wait, what am I saying? Did I say that wrong before? Oh, sorry about that. I just caught myself. While I was erasing, I might have said we know log of 0 is 1. I had everything backwards. Log of 1 is 0 because e to the 0 is 1. I should have paid more attention to what I was saying. We know log of 1 is 0. Logarithm goes through the point 1, 0. E to the 0 is 1. So f of 1 is log of 1, which is 0. F prime at 1, notice also 1 is close to 0.9. F prime at 1 is 1 over 1, which is 1. So we'll find our linear approximation. L of x is f of 1 plus f prime of 1 times x minus 1. So with our notation, I guess I'll put in large parentheses, we let a equal 1. So in all of these, I did specify an a value. So here, the a value is 1, because log of 1 is a value we know. So in general, I don't simplify these, but with zeros and ones, you might as well just simplify that to x minus 1. But here we need an approximation of log of 0.9. So log of 0.9 is approximately equal to L evaluated at 0.9, which is 0.9 minus 1, negative 1/10. So this linear approximation, remember, it is giving us an approximation for the value we want. So I didn't write this in the first example, but just to clarify a little more, I did write it here, that it is giving us an approximation of the function evaluated at a point that we don't know how it evaluates. Here our approximation, negative 1/10, and we should expect a negative for this answer because if you look at the graph of log x, the graph of log x goes through 1, 0, so the log of negative, or the log of 0.9, you should expect to go under the x-axis and get the negative number. Let's do one more. What number do I want to use here? Use a linear approximation to approximate the cube root of 81.01. No, did I say 81? Oh, jeez. I was thinking of the fourth root. I think in the worksheet you're going to have the fourth root of 81. I was looking at the decimal instead of the number when I looked over at my notes. 27.01, sorry about that. Use a linear approximation to approximate the cube root of 27.01. Well, first of all, we know this is going to be close to the cube root of 27, which is 3. So the value we know is going to be the cube root of 27. The value we know is going to let a equal 27 in our notation. So here we're going to take f of x to be the cube root function, x to the 1/3. So what's f prime of x? A third, x to the negative 2/3. And you could write that with the 1/3 cube root of x squared if you want. So f evaluated at 27 is 3. What's f prime evaluated at 27? Well, the cube root of 27 is 3. 3 squared is 9. So you get 1/3 with another 9 in the denominator. 3 and 9 make 27. So here, a equals 27. It's the value we know about. So what's our linear approximation? Well, linear approximation tells us we're going to start here at 3 and adjust it using the derivative. Start at 3, so it equals 3 plus the slope of the tangent line times the change away from 27 in this case. So we need this at 27.01, so what is that? 3 plus a 27th, 27.01 minus 27, so 3 plus a 27th times 100th, which is 3 plus 1/2700. And if you wanted to, you could write this as what, 8101 over 27, or 27 times 3 is 81. or you could leave it like that. So this is one kind of approximation. The next approximation we're going to look at is very similar in that we use a tangent line, but we're going to look at a different quantity on the y-axis. So this next approximation is called approximation using differentials. And we're going to start with the same basic setup. We have a function. We have an x value marked off. We'll call that a. And we have another x value close to a, which we're going to call a plus delta x, meaning that the difference between these x values is delta x. And we're going to see with differential notation, I should say, we're going to define delta x to be dx. More on that in a moment. But what we're going to do is again consider a tangent line at a, because we can find that. Well, now we're going to mark off a couple y values. We're going to use this tangent line to give us some information about this point, but we're not going to look at the entire y value. We're just going to look at how the y value changes from the starting point to the end point, meaning how the y value changes from this one that we know to the one that we want to know. So right here, we're going to call, we have two x values marked off. We have the change in x marked by delta x, their corresponding change in y, we're going to call delta y. I'm going to draw that line a little smaller. So right here, this y change is called delta y. And now what we're going to find using the tangent line is this point right here. That point will be easy to find using calculus because this line is easy to find using calculus. And right here, I hope that shows up on the screen. Right here, between this bottom dotted line and this y value on the tangent line, that is called dy, lowercase dy. And what we're going to find is that dy, lowercase dy, this change in y gives a reasonable approximation for that large change in y. So let's write a couple equations with this. Delta y, what's delta y? Well, delta y is the change in x, so it's f of a plus delta x minus f of a. Let's write it a little smaller so it fits on one board. Delta y is f of a plus delta x minus f of a. So it's the y value here minus the y value here. Well, there's one equation. dy, what's dy? Well, we can find dy. We technically did find dy in our linear approximation discussion. dy was just the latter part of our linear approximation. It was everything except the y value we knew. It's f prime of x times the change in x, delta x, which for our differentials notation we'll write as just dx. You could write it delta x, but I like using the lowercase dx because right here this notation is consistent with our fractional notation for the derivative dy dx is f prime of x. It is not, of course, a fraction. Take Calc 3, the corresponding Calc 3 differential does not work with fractions. But here we can think of our fractional notation as being useful for understanding this equation for differentials. So we have these two equations, and what we're going to find is that dy, lowercase dy, gives a reasonable approximation for delta y. And let's look at two examples. The first one is mainly to illustrate this approximation. I'm definitely more likely to ask you one like this than one like this. But I would like to illustrate these computations and the approximation. So find delta y and dy at x equals 3. I guess I used a. I should say a equals 3, my bad. At a equals 3, if dx equals 0.1 and y is x squared plus 2x. So here there's no function technically defined. I'm going to call this f of x. So delta y is what? Delta y is f. We're starting at 3. We're going to 3.1. So 3.1, f of 3.1 minus f of 3. Delta y is given by this equation. We're looking at x values 3 and 3.1. So what is this? I would not ask you one where you have really tedious things like this. This is really doable. 31 squared is kind of a pain, but what is it? It's like 961, I think. Delta y, this equals exactly, using a calculator. So if I'm using a calculator for something, then it's a large hint that you won't be asked it. So this one is to illustrate the approximation. Delta y is 0.81. What's dy? Well, dy we can do the computation for dy. dy is f prime of x dx. What's f prime of x? 2x plus 2. What's dx? Well, I'll just write it like this. 2x plus 2 times dx. We're evaluating at x equals 3. So we have 2 times 3 plus 2, which is 8, times dx, which is 0.1. So we get 8/10, also known as 0.8. So you can see delta y does give a pretty good approximation. Dy does give a pretty good approximation for delta y. But with differentials, it leads to nice applications. Geometric applications, largely. I like the geometric applications of these. So let's look at this example. We can use this approximation or we can use this differential quantity to find an approximation for a change. Well, let's look at this change. Suppose the edge length of a cube is measured to be 5 inches with a maximum error in measurement of 0.1 inches. Okay? Use differentials to estimate the error in using this edge length to compute the volume of the cube. So here our y value would technically be volume. Our x value would be what? Edge length. And we know how we can relate volume and edge length. V equals x cubed. Well, the differentials is going to tell us, so the error in edge length is going to result in a corresponding error in volume. And we could technically find the exact one. I'm not concerned with the exact error. In practice, these numbers could get inconvenient, and the actual computations could get inconvenient, as they did here. And that's kind of inconvenient. But our differentials would our differentials provide us an easier way to find an approximation. And we can see that we can use that here, because our differentials are going to measure a difference in volume given a difference in edge length. So what would that look like? dv equals the derivative, 3x squared, dx. So we need dv, which with edge length 5, with error 1/10. So you get 3 times 5 squared times 1/10. And what is that? That's 75/10, which is what? Take a 5 off them, 25 halves, not 25, take a 5, 15 halves. Or 7.5. Units cubed, inches cubed, I guess I should write it. So right here, we can use these to find nice differences. And remember, the only difference between differentials and linear approximation, we're looking with differentials at a change from the beginning y value. We're looking only up here. The linear approximation was looking at all of this and saying we can approximate all of that using that. Differentials just chops off this bottom piece.